In this video, we're looking at forces in situations of multiple objects being treated as a system. We're going to practice moving between viewing multiple objects together as a system, as one object, versus viewing them as individual objects. And we'll see certain quantities can be calculated from the system approach. Certain other quantities, you need to look at the objects individually to calculate those quantities. So a system, in terms of forces, is any scenario where you have multiple objects moving all with the same acceleration. This could be a box stacked on top of another box, could be boxes tied together with some rope or string, boxes that are lying next to each other, so when you push box A, it pushes into box B. In all of these situations, treating the objects as a system can be helpful and can allow us to solve for some quantities more easily. Keep in mind, when we're drawing a free body diagram for a system, only forces exerted by external objects, forces exerted by objects that are not part of the system, are the only forces that will appear in our free body diagram. We'll see examples of that in each scenario we look at. So here's our first scenario. We have two boxes stacked on top of each other. A person is pushing the bottom box, but we are told that the boxes move together, both having the same acceleration of 2 meters per second to the right. We want to determine the force that is pushing the 10 kilogram box, and also the force of static friction between the two boxes. And just to simplify things a little bit, we'll assume that the floor is frictionless. So there's friction between the boxes, but not between the 10 kilogram box and the floor. Start out treating both boxes as a system, meaning that we treat them as a single object. In this case, our free body diagram has only 3 forces. There's the pushing force exerted by me, the downward force of gravity exerted by the Earth. We're working with both boxes, treating them as one 15 kilogram object. So the force of gravity is the full 15 kilograms times little g. And then the floor is holding our system up. So we have an upward normal force exerted by the floor. We said that there is friction between the boxes, but that is an internal force. The 5 kilogram box and the 10 kilogram box are both parts of our system. So forces exerted by those boxes themselves do not appear in the free body diagram for the system. The 5 and 10 kilogram box also exert a normal force on each other, but again, those are internal forces. They are forces exerted by objects that are part of the system, as opposed to the floor, the Earth, and me. All of those objects are not part of our system. We have our free body diagram. So we can write the sum of forces in the vertical direction, normal force minus the force of gravity. Sum of forces always equals mass times acceleration, but vertically there is no acceleration. So we set it equal to 0, and we can solve for the normal force. Sum of forces in the horizontal direction, that is just my pushing force, equals mass times the horizontal acceleration, the full 15 kilograms, times 2 meters per second. Very easily we find a value for the pushing force. F me equals 30 newtons. So that's the advantage of the system approach. There are less forces that appear in our free body diagram, and so we can usually solve for something fairly easily. But we can't solve for everything. In order to calculate the force of friction between the boxes, we need to look at the boxes individually. So let's do that. Looking at the 5 kilogram box by itself, Earth exerts a downward force of gravity. The 10 kilogram box exerts an upward normal force. And there is a force of static friction exerted by the 10 kilogram box. The 5 kilogram is accelerating to the right. We see that from the original problem. So the horizontal force of friction must point to the right. Friction must be what's causing the acceleration. And this is static friction because the 5 kilogram box is not sliding. It is moving, but it is stationary relative to the 10 kilogram box. It is not sliding forward on the box or sliding backwards on the box. That's why this is static friction, not kinetic friction. Looking at the free body diagram for the 10 kilogram box, downward force of gravity from Earth, upward normal force from the floor, downward normal force from the 5 kilogram box. My pushing force, I am only touching the 10 kilogram box, so this is a force for the 10 kilogram, but not on the 5 kilogram. And then there's a static friction force exerted by the 5 kilogram box pointing to the left. Looking at these individual free body diagrams is a nice opportunity to think about Newton's third law. The two blue arrows here, the upward normal force that the 10 exerts on the 5, and the downward normal force that the 5 exerts on a 10, that's an example of a force pair in Newton's third law. 10 pushes on 5, 5 pushes back on 10 just as hard. Also the two red arrows, the static friction that the 10 exerts on the 5 and the static friction that the 5 exerts on the 10 are also an example of a force pair. Having these free body diagrams, we can write sum of forces equals mass times acceleration. For the 5 kilogram, normal force from the 10 minus the force of gravity, no vertical acceleration. So the normal force that the 10 pushes up on the 5 with is 49 newtons. This 49 newtons is again the normal force that the 5 pushes down on the 10. So that 49 newtons is showing up over here in the 10 kilogram box equation as well. Looking back at the 5 kilogram box, sum of horizontal forces is just the static friction force exerted by the 10 kilogram equals the mass of the 5 kilogram box times its acceleration. Tells us that the static friction force is 10 newtons. That 10 Newton static friction force is a force to the left on the 10 kilogram box. So this would be Fme minus 10 newtons equals the 10 kilogram mass times its acceleration. Solving this, we again find that Fme equals 30 newtons, which it should because that is the same Fme we saw on the last slide. Looking at the objects individually, you can solve for everything we want to know. It is just more difficult. You have more variables and more forces to account for. So it is often easiest to first treat the objects as a system, solve for what you can from that approach, then go and look at the objects individually and solve for any forces that were internal, forces that you could not find out in the system approach. Here's a variation for you to work on. Two boxes stacked next to each other on the floor. You are exerting a horizontal pushing force of 50 newtons, pushing the 10 kilogram box. In this case, there is friction with the floor, so we have a kinetic coefficient of friction, and we want to figure out the normal force between the boxes and the horizontal acceleration. The answers are right here. So go ahead, try to set this problem up yourself. I recommend starting with the system approach. Treat the two boxes as one object. That should allow you to find the acceleration. Then go back and look at the objects individually. And for either object, if you look at it individually, you should be able to figure out the normal force.